Hey YouTube, Ethan here. Today we're going to be taming volcanoes and turning the instant incineration magma into free power and resources. Volcanoes, whether it's a minor or regular volcano, is pretty intimidating to come across if you've never dealt with them before. The info screen will tell you that the magma erupts at 1726 degrees Celsius. However, volcanoes are not that difficult to tame, and we're going to go over two methods in this video to tame these volcanoes. One is going to be very easy, and the other one is going to be slightly more complicated that includes some bit of automation, such as the one you see on screen. Now, why would you want to deal with these volcanoes in the first place? Well, first of all, the magma at 1700 degrees Celsius is going to provide an insane amount of heat that you can use to power steam turbines, which is essentially free power for your colony. The second reason is that the magma will eventually solidify into igneous rock at 1409 degrees Celsius. Igneous rock is extremely valuable because you can feed it directly to your hatches for infinite barbecue production for your entire playthrough. If you have barbecue production taken care of, you can start making something like the serpent turf relatively easy to provide a very good quality food for your duplicants for that extra morale boost. One thing that we have to be wary of is that the igneous rock is going to be extremely hot once it leaves the volcano, so there's going to be a way to cool it down, and we're going to go over that method as well. This video will be broken up into three parts. First, we're going to talk about how to discover the volcano, then how to tame it a very easy way, and then we'll get into some more automation methods like this. So let's get started. The first thing that we need to go over is how to find and locate these volcanoes. Whenever you're digging around your asteroid, you're going to see these neutronomium tiles. These usually blend in pretty well, but you can use two overlay screens in order to find out where they are and what they are. The first is the temperature overlay. These neutronomium tiles are always going to appear as very cold, so they're going to show up blue no matter where they are. The only place where this is going to be somewhat difficult to identify is going to be in a cold biome. Once you locate the neutronomium tiles, there's a very simple way to find out what's buried underneath, and that is going to your priorities tab, setting it to top priority, dragging your mouse over, and it will tell you in the top left of your screen that this is a volcano. Then you can set it down to priority 1 or whatever you choose. I like to choose priority 1 because then I know it's already been discovered. And from this point on, you're ready to build the existing infrastructure that you see in front of you. The first thing I usually do is build a chamber made out of ceramic insulated tiles. Ceramic is ideal to use in this situation because the magma is going to be incredibly hot. The second thing that we want to do is install a liquid lock, preferably two. Two liquid locks are ideal because one liquid lock will only prevent the atmosphere from the outside of the chamber from coming into the atmosphere on the inside of the chamber. When you use two liquid locks, you can also prevent heat transfer as well. This is because the center chamber between these two liquid locks is going to be entirely vacuumed out, so when the first pocket of crude oil gets extremely hot, it has no way of transferring that heat over to the second pocket and letting all that heat from the magma escape to the outside atmosphere into your base. From there, you're going to want to set up a gas pump so then you can start vacuuming out this chamber. Vacuuming out this chamber is going to be critical because if it's not entirely vacuumed out, your steam turbines may not perform efficiently. If there are gases left over that can block the inlets of the steam turbines, they will not produce as much power as if this atmosphere was already vacuumed out beforehand. Oh, and I should also mention the function of the mechanized airlock. The mechanized airlock allows me to stop my duplicants from coming to work in here if the volcano is currently erupting. This way, in between dormancy periods, I can simply open the mechanized airlock with a signal switch and allow them to come in and make changes to the existing infrastructure or any other work that they might need to do. If this mechanized airlock was not here, the duplicants will be free to come through this liquid lock and come in here whenever, even if the magma is erupting from the volcano. Another consequence of letting your duplicants come in here is that they will pick up the extremely hot igneous rock once the magma solidifies, and they will use it to feed to your hatches or build buildings inside of your base. And you don't want that. The very last thing to do is to command your duplicants to dig up the volcano. Now realistically, you only need one tile in the center of the volcano to remain uncovered so the volcano doesn't erupt. But I like to err on the side of caution and leave a 2x4 row of tiles blocking the volcano just in case I accidentally dig the remaining tile out and the volcano starts erupting before I want it to. So this is kind of how I would leave it until the existing infrastructure was complete, and this also allows you to peek inside and see if the volcano is currently dormant or if it's scheduled to erupt soon. Now this volcano has already been tamed because this is sandbox mode, but if this was a regular playthrough, you just see the idle status, overpressured status, or a dormancy status. If it's dormant, you can go ahead and analyze it as quickly as possible so you know how much time you have before it starts erupting. If it's idle or currently overpressured, that means it's in its active period, and you might want to approach with caution. This is technically all that you need in order to block the volcano from erupting. So you could expose it a lot farther than you just saw, but as I said, I just like to err on the side of caution and leave the entire 2x4 brick just in case I accidentally uncover it completely and I don't notice it, and then the volcano ruins my build. Once you get this far with your volcano, you want to make sure that there's nothing inside of this room that is off-gassing polluted oxygen or other gases. This is because it's going to keep your gas pump working indefinitely or until that material stops off-gassing. So go ahead and get your duplicants to clear everything out of here and let your gas pump do its job. Once your gas pump has finished vacuuming out the room, you can now go ahead and start building the infrastructure to tame this volcano. So let's go ahead and look at a finished tamer and talk about what's happening and how to build it. Here we have our most basic volcano tamer. On the right is a volcano that's going to erupt in 5 seconds, and on the left is a minor volcano that's currently not going to be erupting. So for the purposes of this tutorial, just imagine that this wall is actually this wall, and that only one of these volcanoes actually exists. Both setups are exactly the same despite the minor differences that you may see visually. The biggest difference is how we're going to cool the igneous rock that's coming out of the volcanoes. So first of all, let's discuss the concept of this volcano tamer. As we've already mentioned, the magma is going to erupt at 1726 degrees Celsius. This room is entirely vacuumed out. So when this magma drops into the water, it's going to create an enormous amount of steam that's going to be picked up by these steam turbines. The steam is going to do 2 things. First of all, it's going to cool everything inside of this room. That's going to include the auto sweepers and the igneous rock that is traveling along these conveyor rails. The second thing is that it's going to be picked up by these steam turbines, turned back into water, and in that process, the steam is going to produce a ton of power for us. As this process is happening, the magma is going to solidify into igneous rock because the heat is being removed by the steam turbines. Once that happens, the igneous rock will be picked up by the auto sweepers and placed into the conveyor loader. As the igneous rock is traveling along the conveyor rails, the steam is going to help cool it farther, and we have a conveyor shutoff at the very end, controlled by a conveyor rail thermal sensor, which is going to prevent the igneous rock from leaving until it reaches a desired temperature. For us, this desired temperature is 150 degrees or below, and this is going to give us the ideal range to send it farther into our cooling network. From here, it would travel along these metal tiles, which are already pre-chilled by the aqua tuner. If we take a look at the temperature overlay, you can see just how cold these metal tiles are. As the igneous rock travels along this conveyor rail, it's going to cool down rapidly because of the metal tiles, and it's going to stop at the conveyor chute, which is also controlled by a conveyor rail thermal sensor. This conveyor rail thermal sensor is going to cool the igneous rock down to 25 degrees Celsius, at which point it will open the conveyor chute, drop the igneous rock at the bottom floor, and allow our duplicants to pick it up and use it within our base. Now we could also cool this a lot farther if we wanted to. We could cool it down as low as -1 degree Celsius, which is the current temperature of the metal tiles. But that's a little bit overkill, and you're probably going to make your base too cold, especially if you're relying on things like bristle blossoms in order to feed your colony. However, if cold isn't your concern, feel free to cool it down more because this is going to provide an incredible amount of passive cooling for your base. Obviously, the aqua tuner is going to be pumping polluted water, which is first going to run through the steam turbine room and help cool the steam turbines so they're running at optimal efficiency. It's then going to come through the chamber and then overlay across the metal tiles, starting from the very end and making its way over to the chute. Once at the end, it's going to head back into the aqua tuner, but not before passing a liquid pipe thermal sensor, which is set at 0 degrees Celsius. This liquid pipe thermal sensor is going to tell our aqua tuner when to turn on or off, so it's not running constantly and freezing the polluted water inside of this pipe. We're using a few temp shift plates here. Let's go over what they do. This temp shift plate at the very end is going to help turn the water that is coming out of this liquid vent from the steam turbines back into steam. This side of the chamber will not get as much heat as the middle does. There's going to be some water pooling here, which we want to turn back into steam and make use by the steam turbines as quickly as possible. The temp shift plates that are behind the auto sweepers and the conveyor loader are there to help keep these buildings cool as they're operating inside of this room. They may or may not be necessary depending on the proximity of your volcano. If you decide to copy this exact setup, I found them to be necessary. However, maybe you could move them farther away in a different configuration than you see here. Obviously, that alternative would mean that you don't have access to all of the igneous rock that gets deposited by the magma. So you may have to send your duplicants back in here during a dormancy period in order to pick that up. Don't forget that these volcano tamers are highly customizable. All you have to do is wait for a dormancy period to send your duplicants back in here, especially if you've already pre-planned a mechanized airlock at the entrance to do that. There's also a temp shift plate behind the aqua tuner, and this helps turn the water back into steam because this area of our chamber is not going to get nearly as hot as this area where the magma is flowing. Finally, the very last critical component of this chamber is this divider. This divider is going to prevent the magma from flowing into the aqua tuner, which is built out of steel. This aqua tuner is going to overheat at 325 degrees Celsius, and as we already know, the magma is incredibly hot and would destroy this almost right away. And obviously, while magma is present, your duplicants aren't going to be able to come in here very easily in order to fix it. So this divider is essential for this type of setup. Now, just before we get started and let this configuration run, I want to quickly gloss over the minor volcano setup that I have here. It is definitely possible to cool the igneous rock that is coming out of the volcano with polluted water. In fact, you could also use other types of liquids that can be cooled much lower than polluted water if you choose to. The biggest difference that you're going to want to be aware of is that your conveyor rail thermal sensor cannot be set higher than the evaporation temperature of the water that you have in this chamber. Remember that polluted water is going to evaporate at 119 degrees Celsius. So if you're sending in igneous rock that is 150 degrees Celsius, like we are on the right, chances are it's going to start evaporating this water very quickly. So this is why I like to go with metal tiles instead. But if you don't have metal tiles available for whatever reason, or if you don't have the resources, you can certainly go with a liquid. Just be sure to follow that guideline so you don't evaporate the liquid, because then your whole build will be a bust. So let's go ahead and let it run. As you can see, right away, the water is going to turn the magma into igneous rock, and it's going to start heading down the conveyor rail at a very hot temperature, almost 1200 degrees Celsius, as it's entering the conveyor loader. This gets cooled down relatively quickly, as you can see by the tooltip overlay over the conveyor rail that is right beside the volcano. Already you can see that the steam turbines are working at almost maximum efficiency, and as the water starts to get hot on top of the aqua tuner, the far right steam turbine will eventually reach maximum efficiency as well. These steam turbines will continue to produce full power for your entire colony as long as there's heat present in this chamber. Don't forget that we're not only getting heat from this magma, but we're also getting heat from the igneous rock that is on the conveyor rails, which, like I said, does cool relatively quickly and will eventually go through this conveyor shutoff. It's also worth pointing out while we're here that the conveyor shutoff does not have an overheat temperature. As you can see, this one is made out of copper and it's working just fine, and it was just recently engulfed by the magma. So if you're desperate for steel, you don't have to build the conveyor shutoff out of steel. In fact, not everything inside of the steam room is built out of steel. If we take a look at the metal overlay, you can see that there is some copper involved, even right beside the volcano. Nonetheless, if you've ever come by to my streams, you know that I don't mess around with building these things out of lesser materials. I like to use steel whenever possible, even if it's considered to be a waste. To me, I would much rather have this Volcano Tamer work consistently and not have to deal with overheating issues to an area where I thought that cheaping out on metal might work, when I could just build everything out of steel to begin with and making sure that I have the best possible chance of having it work the first time. Some things that absolutely have to be built out of steel, however, is the auto sweeper, the conveyor loader, the aqua tuner, and the conveyor rails that are exactly over top of the volcano, because these are going to be experiencing the most amount of heat in this entire build. Don't forget that the auto sweepers, conveyor loaders, and the aqua tuners produce their own source of heat as well, on top of the already very hot temperatures inside of the steam room. So give them the best possible chance of success and build them out of steel so you don't have to get your duplicants to come back in here and fix it or reload the game. So we're not going to wait for the igneous rock to cool down all the way to 150 degrees, so I'm going to set this a lot higher so you can see the igneous rock go through the conveyor rail and how efficiently the metal tiles can cool it. Let's go ahead and set this to 250 degrees and watch the igneous rock as it travels through the conveyor rail across the metal tiles. You can see that it's passing through, and if we look at the temperature overlay, the metal tiles do start to heat up quite a bit. However, there's so much cooling happening on these metal tiles that it starts to drop the igneous rock at 23 degrees Celsius almost immediately. But eventually, the heat will be overwhelming and it will be stopped by the conveyor rail thermal sensor, so the aqua tuner will have to work harder in order to continue to cool the igneous rock that is present. Now, one of the major positives, but also downsides to this build, is that the steam turbines are going to be working at 100% capacity at all times. There's absolutely no check on these steam turbines to make them work any slower than they are right now. This means that they're going to use all the heat from the magma at the fastest rate possible, which is going to give you arguably the best ratio of igneous rock production out of this volcano. So if that's what you're trying to go for, then great, you can stop here. But if you're trying to get optimal heat production turned into power from this volcano, you're going to want to add some automation in order to do that. So let's take a look at a slightly more advanced build on how we can adjust when these steam turbines turn off and on so we can make the most of this heat that's coming out of the volcano. Here we have a slightly more high-tech Volcano Tamer, and this is going to prioritize using all of the heat possible from this volcano magma than the previous build that we just looked at. This actually isn't as complicated as it looks, so let's go over exactly how it works. First, we have our magma chamber. Once the volcano starts erupting, it's going to squeeze through this one tile block, and the magma is going to be blocked by the mechanized airlock that's built out of steel until certain automated intervals allow some magma to drip into the steam room. Once it drips into the steam room, these window tiles made out of diamond are going to transfer the heat from the magma into the steam room and start boiling the water. Then, just like before, the water is going to turn into steam and turn on the steam turbines and start producing a lot of electricity for your base. In this scenario, the steam turbines are going to be turned off and on by the smart battery that's connected to them via automation. This is going to allow them to stop extracting heat once the battery is completely full, and you can connect this to your main power grid, or you can have it self-powering this Volcano Tamer in the exact same way that a SPAM would self-power itself. The reason why this looks a little bit more complicated than the previous build is because we have certain game mechanics that we have to try to avoid in order to keep this functioning 100% of the time without having to send duplicants back in here to fix it. First of all, once the magma drops in here, it's eventually going to solidify into a natural tile. So we have to have a robo-miner in here that has access to that space in order to mine it out. Second, we have to have an auto sweeper in range that has access to that igneous rock that's just been mined out so it can load it onto the conveyor rail. From here, it's the exact same as before, and the conveyor rail is going to extract as much heat from the igneous rock as possible, and in turn, it's going to cool the igneous rock before it gets to the conveyor shutoff, which is once again controlled by a conveyor rail thermal sensor. And from here, the process is exactly the same. It's going to go through a cooling conveyor belt loop until it gets to the end, where a chute is also controlled by a conveyor rail thermal sensor set at 20 degrees Celsius. Now, of course, you can make this cooling chamber as big or as small as you want depending on your needs. There are also some notable things going on that are not present in the previous steam room. First of all, we have a temp shift plate that is connected to the window tile and some metal aluminum tiles inside of the steam room. The only real purpose of this is to help bump start the steam production. Because this room is entirely vacuumed out, the magma's heat cannot transfer into the water and start producing power. So we need to connect it via a temp shift plate and metal tiles to the water so it can bump start that steam production. Likewise on this end, I have two metal tiles which are very close to the conveyor rails that the igneous rock is traveling beside. This is also connected to the water and it's going to help bump start the steam production. Finally, let's go over the automation. The automation is pretty subjective. You can set this up in a number of different ways. Let's start with the thermal sensors. These thermal sensors are going to send a green signal if the temperature is below 200 degrees Celsius. And of course, we're going to be measuring the temperature of the steam. When it's below 200 degrees Celsius, we want this door to open and drop more magma into this window tile pocket. But there's more to it than that. The temperature is going to vary wildly, so we want to make sure that we're not dropping too much magma, because that can cause problems. So these two thermal sensors are connected to an OR gate, and if I get a true signal on one or the other or both, it's going to send a green signal into an AND gate. Of course, for an AND gate, we need two true signals in order to start this mechanized airlock operation. So let's go ahead and see where that true signal comes from. It's going to come from a secondary AND gate. One of the things that I want to check is if there's actually magma down here or if there's not. I have this liquid element sensor looking for liquid magma. If it's detecting magma, it's going to send a green signal, which I want to invert into a red signal. If there is no magma present, that's the only time when I want this mechanized airlock to open and drop more magma down. If there's already magma present, then I don't want to open this door and drop more magma on top of it. Now, the third criteria to all of this going on is a timer sensor. Timer sensor is important because I only want drops of magma coming down from this mechanized airlock. So you can see right now all of the additional criteria is being met. There is absolutely no steam, which means the temperature is below 200 degrees Celsius. There is no magma, so I'm getting a red signal, which in turn gets turned into a green signal, indicating that the mechanized airlock can in fact open. And finally, this timer sensor is going to allow the gate to open for only a split second, so only a very small amount of magma is able to drop down into the window tiles. Let's watch that again. It opens and closes very quickly. This is just long enough for a little bit of magma to come down in here. This additional infrastructure off to the side, its only purpose is to consume power from the battery because we're going to be disconnecting this entire setup from the rest of our base using a power shutoff. So obviously, this section is absolutely not needed for your build. So let's go ahead, start it up, and let it run. Now, because this volcano doesn't erupt for another 7.6 cycles, I'm going to manually brush in a lot of magma into the magma chamber. You can see that the magma gets pushed up against the door, and when the timer sensor tells the door to open, it's going to allow some magma to drip into the steam room. Once the magma starts dripping, this window tile is going to heat up extremely fast, and it's going to transfer some of that heat over into the metal tile that is connected to the water. Let's go ahead and fast forward a little bit so we can see this start to happen. Okay, the metal tile is getting extremely hot, and pretty soon we should start to see some steam. And here comes the steam. Once the steam starts working, it's going to allow the rest of the water to become hot, and also these metal tiles are going to heat up extremely quickly, which are also connected to the water. From this point on, it's not long before we start to get action from our steam turbines. But before we have that happen, we have to disconnect it from the rest of our grid and turn our sun lamp on. So now that the sun lamp is draining power, our steam turbines are going to be allowed to refill the battery, which is controlling the steam turbine production. You can see that the thermal sensors are activating depending on the temperature inside of the steam room. When the temperature is too low, it's going to keep the thermal sensor on, which will send a constant green signal to allow this mechanized airlock to turn on. But of course, the mechanized airlock cannot turn on until the other two criteria is met. First of all, I need magma present here, and if there is no magma, it will send a green signal, which will allow the mechanized airlock to turn on, but once again, only when the final criteria of the timer sensor is met. So you can see how it constantly drips magma down in here in order to keep the steam room at optimal temperature. This means that you're going to be able to preserve the magma that is coming out of the volcano for a very long time. One thing that is very important about this build is that you must have this little chamber in here in order to provide place for the extra magma to go once the mechanized airlock closes. When this is closing, it wants to push the magma to the outside of this chamber. But if you have a little crevice in here like you see, it will push the magma on top of this little crevice and it will just basically sit here for your entire game. Let's go ahead and jump to the future and see how this volcano works. As you can see, the magma is nearly overflowing over top of the volcano. So one of the things that you may want to change, depending on how you build your volcano chamber, is to make this magma area a lot larger. In fact, it might be worth it to build this whole area down a couple tiles lower so that you have room to collect more magma as your playthrough goes on, unless these steam turbines are going to be your main source of power, in which case you're going to probably be using a lot more magma in order to keep the steam room at optimal temperature. In a very mature colony, obviously you're going to have very high power requirements, so this magma may actually be used up a lot quicker depending on what other sources of power you have in your colony. One thing that is worth noting is that every single chamber in here has to be vacuumed out in the exact same way as the first build that I showed you is. If you have any pockets of polluted oxygen or any other type of gas that is blocking these inlets, these steam turbines are not going to be able to produce power as efficiently. In addition to that, you definitely want to make sure that these areas are completely vacuumed out so that the magma can flow easily and unobstructedly into the window tile area. As you can see in this scenario, we don't have the thermal sensors turning on nearly as much because we have so much heat here from the igneous rock, and this igneous rock is also very hot, which is transferring heat into the steam chamber. So the magma isn't flowing nearly as much as when I first started this scenario. One of the benefits to this type of scenario than the previous build that I showed you is that your duplicants can probably come in here comfortably in an Atmos suit if you have a liquid lock that allows them to do so. This is because there's no immediate magma presence in the steam room as there was in the other chamber, which is combining the steam room into the lava chamber. Here, both chambers are entirely isolated. Now, ideally, your duplicants shouldn't have to go back into the lava chamber, but they can definitely expand this room if needed without having exposure to the magma. So let me go over all the overlays so you can see how I set this up, and I'll give you all the values for the automation as well. Here is our power overlay. This is the temperature overlay. This is the material overlay. I'm using steel conveyor rails once again. All of the buildings down here are built out of steel except for the conveyor shutoff, which doesn't have an overheat temperature. The metal tiles are built out of aluminum. The window tiles are built out of diamond. And I even went ahead and built the thermal sensor and the automation out of steel as well. This is the plumbing overlay. I'm using the conductive panels to cool the steam turbine and the battery because this room is entirely vacuumed out. The cooling once again prioritizes the aqua tuners to make sure that they're running at optimal efficiency. And only after that, it comes into the cooling chamber to cool the igneous rock. The liquid pipe thermal sensor is set to send the green signal if the temperature is above 0 degrees Celsius. There is no ventilation. And finally, this is the automation. Like I said before, this entire area is going to be redundant for your build. This only exists to consume power. The first set of automation is controlling the steam turbines from the smart battery, which is set to 40% at a low threshold and 90% at a high threshold. Both thermal sensors are set to send a green signal if the temperature is below 200 degrees Celsius, which are connected to an OR gate. The OR gate outlet is connected to an AND gate input, and the outlet of that AND gate is connected to the mechanized airlock. The second input of the AND gate is connected to the output of another AND gate. And the two inputs here, the first one is connected to a timer sensor, and here are the variables. And finally, we have our liquid element sensor, which sends a green signal if it's detecting magma, which is then inverted to send the opposite signal to the final AND gate. Our conveyor rail thermosensor at the bottom is set to send the green signal if the temperature of the igneous rock is below 20 degrees Celsius, and that is connected directly to the conveyor chute. So I hope that you enjoyed this video on taming volcanoes and oxygen not included. If you did, be sure to leave a rating on this video, as this helps me out immensely in the algorithm. Also, be sure to subscribe if you'd like to see more videos like this in the future. And leave a comment down below telling me what you thought of this tutorial, if it was able to help you out, if there was something that I missed, or if you have a topic that you would like me to cover in a future video. If you haven't been to my live streams yet, I highly encourage you to come out and hang out, where we play Oxygen Not Included every Friday and Saturday night. We're working on our super duper Dreamland asteroid right now, and we're making some great progress towards space. So come hang out or check out the VODs if you would like to see more Oxygen Not Included content. Thank you to everyone who's supported me through this YouTube journey so far, and I hope to see you stop by at some point and say hello. I'm Ethan, and I'll see you guys in the next video.